1, 2, 3, 4, 5. Is the sound working okay? Morning, everyone. Morning, everyone. Can you hear me? I've had various shenanigans with my audio setup. Nice to know that you can hear me. Thanks, Chris. Good morning.
Five, four, three, two, one. Thunderbirds are go.
Good morning. Apologies for that. But, need something to cheer us up some of these mornings. Right. Where am I? I'll get smoother doing some of this stuff as I do it more often, I guess. Let's start recording on Blackboard. It is being recorded on YouTube anyway, so yeah. Good morning, everyone that's joined in. What I'm going to be doing today is using a little bit of what we've been doing the past couple of weeks. So we're going to kind of go back to what we did in the first week, a little bit of curve fitting, and we're going to set it up as a problem in solving a set of simultaneous equations. Do jump in with questions and so on when you've got them. It makes everything more fun. Okay. Other things, I should send around another announcement. There is another short assignment that should have popped up in the assessments tab. It's basically on the material that will be in this lecture. Please submit the previous one by 3 o'clock this afternoon. Other than that, I don't think I've got any big announcements. I still promised a little bit of extra stuff on C++ and how to use the LU or other solvers in the Eigen library. I'll see, maybe I'll do that at the end of this lecture for people who are interested in that, or perhaps I'll record it separately. Okay. So, got to put my fancy cursor on, but I think perhaps that's okay for now. Okay, so it's week 4 somehow, and I put curve fitting 1. If you remember, in the first week we did a little bit of an example of how to code up linear regression I more or less just gave you the expressions. This time I'm going to try and extend it to general polynomial fitting, so fitting a quadratic or a quartic, or indeed any size problem that you fancy. And what we'll end up doing is building a matrix, populating it with some sums, and then solving the resulting equations using what we learned in the past 2 weeks about linear equations. So it also bring everything together that we've done so far. The way I'm presenting this here is a little bit sort of ad hoc. And so what I'll do next week, or possibly in the Friday, but probably next week, is give a slightly more systematic derivation of these equations using a sort of more obviously matrix type representation. But we're just going to sort of write out the equations and look at them and convert them to matrices sort of by inspection this week. Okay, so this is the material from lecture 1. So what we did is we set up our problem. We had some actual data. Someone sat in a lab or has gone and scraped the internet or something, has got a set of data, y, and they've got a subscript I. So there's n pieces of data, and that typically go from, you can see my sum here, from 0 to n minus 1. I've got n pieces of data. And in the lecture we had on lecture 1, we assumed that it should fit to a model of an intercept. In other contexts, it's sometimes called a bias, some sort of thing that just shifts the average level of the data, and then straight line. So we've got this other measurement that's been made of how far along the x-axis it is, and it's assumed that this measured y value should just be a straight line with slope a1 times the x value plus the intercept. And onto that, there could be a random error. So whoever's making the measurements perhaps didn't do it perfectly for whatever reason. It's very rare to actually get perfect data. So obviously we can rearrange for the error, and a better way of trying to minimize the error will be to look at the sum of the squares of the errors. So if we add up this, we get that. And I'll note for next time, this thing here is actually the dot product, the error vector with itself. So I've got these I measurements. So if I write a vector containing the different measurements, if I dot it with itself, that's what I'll get here. So what we're actually minimizing is the length of the error vector. We're going to work out an expression for that more clearly, but let's just sort of dive in. What we did is we wrote this out, and then we said, well, our yi and xi are measurements. What we're actually doing in this is tweaking the a0 and a1 parameters to get this thing minimized. So the length of this is a function of a0 and a1. So if we want to minimize the function, what we did, I'll write it out again in a second, was to take partial derivatives with respect to a1 and a0, set them equal to 0. This gives us two simultaneous equations, which we could then rearrange, and we could get expressions for a0 and a1. And you could also look at the correlation between the data, which is the covariance divided by the standard deviations, and that will give you this sort of R value, a measure of the fit that you can also get from Excel. But just some useful formulae there. And I put up these sort of exercises there. So that's what we did in week 1. Now let's think what happens if we have not just a straight line, but some general polynomial. So I've got my data points. I've got the same set of data points. I mean, obviously different data set, but I'm calling them y again. I've got n values labelled by this ith index, and they should be related to the measured x value by intercept, slope, but then these other coefficients which give the coefficient of the polynomial term of degree n. We start with a0, and we could think of this as x to the power 0, then a1, x to the power 1, a2, x to the power 2. And again, we've got an error at the end. We do exactly the same thing. We construct the length of our error vector is the square of this thing rearranged to make ei on e as the subject. And now we go up to n. We've now got I've been a bit naughty. I should have a different numeral. So I was keeping this little n before for the number of data points. This is not necessarily the number of data points. This could be something different. It's a different the maximum order of the polynomial. And so whatever that is, this will be a function of those parameters in our fitting model that will control how good our model is. And so we then take the partial derivatives with respect to those parameters. And so if we take the derivatives with respect to all those partial derivatives with respect to all those parameters, set them equal to 0, we'll get a set of simultaneous equations. And we know how to solve them, so we can do that. So, for instance, let's take a quadratic function. We assume our data is going to be modelled by, I've written it out explicitly this time, that it will be this bias, this intercept, this offset, times 1, or x to the power 0, plus a1 times the slope, and then this quadratic term, and an error, rearrange. And then, if I take the derivatives with respect to a0, a1, and a2, I get these three equations. So it's taking the partial derivatives of these functions. I'm remembering in these cases that x is not a variable, it's our measurements, the same for y. So essentially I'm going to get a sort of chain rule term. Do this and I get three equations. And if I look at what I've got these sums which are really coming from this length of the vector, dotting it with itself. So I'm adding up the components, if you like. We'll look at that a little bit more next week. But these are the three equations I get. And what you can see is that the right-hand side doesn't involve these parameters. It doesn't involve the things I'm fitting, a0, a1, or a2. So there's a right-hand side, three terms, and I can write that as a vector. That's my right-hand side vector, or the part of the augmented matrix that goes on the right-hand side. Those sums there. They're mixed terms between the y and then the powers of x. So it's just the sum of y, sum of x times y, and the sum of the square of x times y for each of the data points. And this equations on the other side, I could write as a square 3x3 matrix. So I've got three parameters, a0, a1, and a2. So I've got square 3x3 matrix. And then I could write in another vector here, a0, a1, a2. And that is my x. Here, what I'm saying. But this three set of equations I've got, the three equations I got by doing the partial derivatives with respect to a0, a1, and a2, and setting them equal to 0 because I want to find the minimum. I can write these out in the form A. The A matrix is 9 values are going to be these things in the curly brackets on, round brackets on this side. Then the X will be A0, A1, A2. You can see when you multiply them out, this is what you would get. And then the right-hand side, the B vector, is going to be those. So that's the recipe for doing a quadratic fit. What you need to do is to get your data into the computer, in a way that you can access, as we did before, so doing these sums. Then you've got to calculate these things. You can see that they're kind of ordered in terms of sets of different powers of x. In general, next week we'll sort of generalize this and we'll call these things actually basis functions. So instead of polynomials, we could actually use sine functions, cosine functions, exponentials. There's lots of different things we could use, Gaussian functions. But we're going to stick with polynomials for now. And once we've got ax equals b, we use one of our solving techniques, whether we use Gauss elimination or we use LU decomposition. Any of the other methods we want to use, and we should be able to solve. And yeah, so that's quadratic. And we can extend this as well as having some powers of our variables. We could have several different independent variables. We could have a A1, A2 and A3, so it's 3 measurements along different axes, if you like. And we make those measurements I times, and we got a final result. So this measurement is assumed to be a function of different variables. And we would just go through and do exactly the same thing as before. Write out the equations, take the derivatives with respect to the coefficients. It's still linear in the coefficients. It doesn't matter in some sense. We've got these different variables, these different x's. We can still write out an ax equals b. So I've given you some data, little exercise if you want to try and write out the simultaneous equations, convert them to matrix form, fit it up and do it. I will try and remember, I'm sometimes a bit forgetful about putting answers up, but if you plot the data and then plot your line, you should see whether you've got it right or not. And just a little thing to think about. If you've got data that's not a linear sum of terms, but is actually a product, you can actually still convert this into a linear problem using some maths that you know. So have a little think, see if you can decide how to do that. So that's the material I wanted to cover. Somehow I'm missing a slide I thought I was in here. I've got a quadratic function. I've just included that at the bottom. Apologies. If you look at the assessment on Blackboard, you'll see that as well as fitting a quadratic, I ask you to fit up a cubic. So please sit down with pen and paper, write out these simultaneous equations, get them into matrix form so you're satisfied with what's going on. And include that in the working, but then fit up the cubic fitting data and do the same thing for a cubic problem on Blackboard. So on Blackboard you'll find sort of a general question, a quadratic fit and a cubic fit, and upload your working. So that's there. Again, I talked a little bit about numerical recipes and how to access the site last week. It's at the end of the second lecture. Another reference, there's also loads of great stuff on the internet as well. Plenty of places you'll find these derivations. So we suggest you go through them and really get sorted in your head what's the variable, what's input and output data, how you do the fitting. So that's all I wanted to say as a sort of lecture-y type material. It's a bit shorter this week. I think previously it's tended to be sort of extended because I've talked about lots more about getting the computers up and running. Another thing that would be very good today would be if anyone is having problems working at home, if they haven't managed to get any of the Python or C++ up and working on their home computer, it would be good to let Chris and I know, and we can try and help you get a working setup. because obviously we're not quite sure what's going to be happening later this week. So it'll be good to try and make sure that you're ready to, if needed for a period of time to work from home, that we can support you properly and practice sharing the screen and that sort of thing. Okay, I'll try and get out the habit of clicking my tongue as well. I don't know where I've got that habit from. Recording yourself is an amazing way of realising the number of irritating habits you've got. So do call me up on pulling the beard and clicking my tongue. I'll try and cut it down. That's what I wanted to say from the formal part. I'll let you get on with the different exercises. Please ask questions, and then maybe I'll do another little bit about using the solvers and eigen in C++ live, or perhaps I will consider just taping that offline, and I'll probably do that just to sort of ease myself into it a little bit. So that's wrapping up this. Thank you for listening, if you have been. Absolutely, Claire. Yes, that's one of the big advantages. So I did try to emphasise in week one that whilst I'm not directly assessing, I do want you to include the working when you submit the assessments. That allows me to give you some partial credit. But the main reason is that then you've got a source of stuff that you can go back to during the time controlled assessments. So again, I said in week one, the time controlled assessment for this one is not going to be sort of a 2-hour thing. I'm going to give you a couple of days. I'll give a slightly extended problem, maybe fit up a data set, find the best model, compare different ones, explain how you've done it, for instance. So you'll have a couple of days to work on it. But obviously, if you've got your previous assessments, if you've got the logbooks there and so on to work through, it should be beneficial to you. Question from Tom about the formats of the submitted file, the thing the working essentially. Yeah, I'm basically happy with any standard one file form. There's 70 odd homeworks, so I've got to download them, unzip them, open them up in multiple programs. It just sort of multiplies my time. So if it's a single file, I can tell Chrome or Firefox to just open up in one place and look at, and makes me happier. So an HTML file serves that purpose, Word document serves that purpose, PDF serves that purpose. If you're not sure, ask me and I'll say that I'm happy or not with it. Yeah, I'll emphasise again that please do make sure that you can attempt the questions at home. If you don't have a setup at home where you can do stuff, let us know. Help you. That can potentially include loaning of laptops or helping you buy for money for it. Please do that. Chris and I will be here, obviously, if you've got any questions. You can also reach out to me on Teams. My preferred method for any questions that are slightly general be the discussion board on Blackboard. I'll try and remember to check it. Perhaps I'll try and update when I do check it, because then it can it's a benefit to everyone. It's better if my answers go to everyone, so people don't get more help or less help depending on how shy they are asking. The spooky background is actually West Common. Those that live in the West of Lincoln. Right. Sake, let's get up Visual Studio. Code example of doing the LU solver in Eigen. I've got it here.